Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so let's get started. I'm really happy to introduce Pierre-Yves Strube. Pierre-Yves is a postdoc at the MSR INRIA Joint Center in Orsay, and we've been working together on the F-star project. Pierre-Yves has been our Coq expert in this project, and he's going to tell us today about some work that's not so related to F-star, but more his work in his PhD related to extending Coq with decision procedures in a tool called Coq modular theory, which is going to be part of the next release of Coq. So this is going to be in the main line of Coq 9. So, Pierre-Yves.
Okay, thank you. So let me start to introduce this talk with formal methods. So formal methods are tools for proving correctness of programs. And as of today, we start to have some big programs verified using formal tools. So for example, you have some OS kernel verification. In Coq, you have the CompStat project, which certified C compiler for a big subset of C. And you have also the AS3 static checker, which is used for checking the absence of runtime error in some controllers of the Airbus A380, for example. And the idea here is that formal tools are complex programs too. So why should I trust the machine this time when I'm using a formal tools, since I don't trust the machine for my other complex program? And so the idea is that you want your formal tools to produce either a certificate that you can check in the simple verifier, or either to be small enough to be read and trusted, like no more than 5,000 lines of code. And the Coq Proof Assistant is such a reliable formal tool. So initially, the Coq Proof Assistant was designed to develop mathematical proofs. And so what you can do with it is that it allows you to write formal specification and to programs, to write programs and to prove that the programs comply with that specification. And why the Coq Proof Assistant is reliable, it's why you have the Coq Proof Assistant is separated into two parts. First, on the top here, you have the proof checking part. This part is split into two subparts, which is a formal language, which is not a program, but which is the logic you are using in the proof assistant. And then you have the proof checker, which is given a proof, a certificate, will check that this is indeed a proof for the property you want to prove with relation to the formal language. On top of that, you have the proof construction stack. So this one is bigger. Here you have a proof engine. So a proof engine is a very low-level program which allows you to, from some commands, to build some proofs for the proof checker. Then you have the proof development language. So this one is a high-level language for proof constructions. And for these two parts, you are able to build some libraries of theorems that then you can use for more extended development. And so the idea here is that to trust your proof, that to trust that the proof checker is in the whole stack is doing the job, you only have to prove that part. That is the final part which tells you that is your proof, your final proof is correct or not. And this part in Coq is small. It's less than 10,000 lines of code of ML. This one is bigger. It's between 100 and 200,000 lines of code. And if you have a bug there, then the proof checker will detect it and reject your buggy proof. So here is a more broader map of the ecosystem of formal tools. So on this line, you have the power of the formal tool, going from memory safety to functional correctness and to formal math. On that line, I have the.
Can I ask what you do differently, formal math and functional correctness?
For functional correctness, I won't be able to speak about mathematics, for example. So this is, for formal maths, I have set theory, which is more expressive than what I can express in a functional correctness formal tool about, okay, my function is taking some input and returning some input obeying a predicate. With that, I cannot encode the whole set theory, for example.
Okay, sure.
On that axis, I will have automation. So starting from fully automated tools to fully interactive one. In the middle, I have a gray area where I am between interactive and automated proofs. So for example, ML checking is fully automated. Okay. ML checking is decidable, but what you obtain is some memory safety. If you move to the gray area, so this is a kind of trade-off, you can obtain functional correctness is quite an automated way. And for example, so you have VCC, Boogie, and for example, F star, we worked on with Nikhil is here. It's a trade-off between what you can do automatically and what you can prove in the system. And then here you have Coq. So in Coq, you are nearly totally interactive. You have few automation in Coq, but you have a very large logic. You can express quite a lot of things. But now I want to zoom on Coq, because Coq is not only one logic. Coq now is 25 years old, and there have been some work about the logic. So the very first version of Coq was the calculus of construction there. So in the calculus of construction, for example, it was not possible to have a built-in definition on natural numbers, for example. So you had to do a lot of encodings. And then, for example, addition was not a function. You have to prove, each time you want to prove that 1 equals 1, 2 equals 1 plus 1, you have to apply some rules about your encoding. And then you have this new version of Coq, which is a calculus of inducting construction where you have inductive types. And then here you are able to define quite a lot of functions defined by induction. And in that case, you gain more automation because you have some computations. You have things that you will be able to do by computation. And you are more expressive. And then you have CAC, the calculus of algebraic construction, where you can add more computation. And you can express more theorems without having to encode them. And so my work here is to continue pushing on that line. You see, the more we progress, the more you are going to the gray area of automation, and the more we are expressive. And here the work is about going to the gray area. So first, I want to say that Coq is not a panacea for studying real programs. Okay? For studying real programs, you want to go here. But it is invaluable for example, certifying the logical foundation of your formal tools. And that's why, for example, I did for formalizing the meta theory of F star, or for formalizing the meta theory of a previous language, which is F7 for cryptography. It can also be used to certify the reference implementation of these tools. So it's why, for example, I did for the certification of the type checker of F star. And also, it is invaluable for formalizing complex mathematics. So you have the group of Georges Gontier proving the face of some theorem in Coq. And for example, currently I'm writing some library about proving properties of elliptic curves after proving some cryptographic algorithm about elliptic curves. So there is an interest here in being able to express more things in Coq. So my talk will be in the...
Can I ask a question about the previous slide?
Yeah.
So for example, when you certify the F star type checker, my understanding is that Coq is a programming language also? And then
no,
you write the type checker inside Coq also?
So it could be, but here no, we define a new methodology where you first do the meta theory, and then you write the type checker of F star in F star. But since F star is powerful enough to express the correctness of the type checker, it's not powerful enough to prove the correctness of the type checker, but to express it is powerful enough. Then you can import the result of the type checker in Coq and prove that type checker is well formed. This is a kind of self-certification. But you could also write this program in Coq and extract it. But as I said, then Coq is not a panacea for doing that thing. because you do not have effects, you have to write strongly normalizing function, and so on. So in this talk, I will first introduce the Coq Proof Assistant. Next, I will describe my new calculus, which I call the calculus of Pressburger constructions. And I will define it. And then I will go to how you can decide proof checking in this new calculus. Then I will speak about kernel security in this extension of Coq, and I will conclude. So what is Coq? So Coq is 4 things. Coq is a programming language dedicated to processing mathematics. Then Coq is a set of deduction rules characterizing the logic chosen for expressing the mathematical statements and also the proofs. Coq is coming with the proof tactics allowing to construct proof interactively, and then on top of this you have libraries of proof theorem. So let me introduce the 2 first points. What is these programming languages and what are these deduction rules? So for that we are moving 1 century ago to Gensen and to natural deduction. So in Gensen natural deduction, the idea is that a proof is a tree. You give up the axiomatization of deductive reasoning and you replace them by inference rules. And for each logical connector, you will have rules for introducing them and rules for eliminating them. So what is the proof in natural deduction? So I said it's a tree, and then you have a goal, what you are proving, which is Q, and you are proving the goal under hypothesis. This PI is here. And each hypothesis will be then justified in turn by subproofs.
You say tree, but the DAG would be just fine, right?
Yeah. So I will focus on the implication connector. So the rule for eliminating the implication connector tells you that if you have a proof of A implies B and a proof of A, then you will have a proof of B. And what this rule is hiding, this rule hides a total function transforming a proof of A, a proof of type A, because I will move to types next, to a proof of B. And this is what is the Curie-Howard isomorphism. You see proposition as types, that is, that proposition will be the type A equals B, and then you see proofs as programs, or programs as proofs. So how we do this in Coq? So in Coq, you introduce a type prop for containing other types. What will be the inhabitants of prop? There will be proof types or propositions. So for instance, if A is of type prop and B is of type prop, then the arrow type from A to B is a proof type, or a proposition for the implication of I in place B. And a proof type is valid, a proposition is valid, if there exists a program of that type. So for example, the function, so this is Coq syntax here, for the function, taking a x of type A and returning x, this function is taking a and returning a A. So this is a proof of A implies A. Now, if I want to move to a full logic for all the quantification, I need some more powerful types. So this is now the elimination for the for all connector. So telling me that if I have a proof of for all x p, then I can derive a proof of p in which I substitute x by t, a term t. And so what you want to express is that a proof of for all xp is a function taking a t and returning a proof of p of t. And what we have here is that the result type depends on the input. And we need what we call then dependent types, that is types depending on the value. So Coq is coming with these dependent types. So what we do is that now you have a type for types, which is a type with a capital T, and then you can define type families. That is, for a type a set A, you will define a family B of I for I being A. And you will see them as functions from A to B. So you can, with that, have polymorphism. For example, you can have list of A, which are the type of the list of elements of type A. And this is a function from type to type. Or you have vector of size n, which are the list of size n. And then here you have a dependent type on values, going from natural numbers to type. And then you can continue. For example, ordinal n is a type of numbers lower than n. And so the same for predicate. For example, prime n is a type for proposition which says that n is a prime number. And this one is going from nat to prop, the type of propositions. And so there is a new type construction, which is a dependent product, which you can read for all x of type t, I have the proposition b, which is basically the encoding of the for all quantification. This is a generalization of the euro type from t to b. So for example, if I want to say that for all natural number, 4 times n is not prime, I will write for all fn of type nat, not, which is a function from proposition to proposition, prime 4 times n. Now, so I'm coming back to my brief introduction to Coq. Now I said that also Coq is a logic, but also it's coming with proof tactics allowing to constructing proofs interactively. That is, I will have proof tactics allowing me from a type of proposition to build a program of that type. That is a proof for that proposition. So Coq is offered with very low-level tactics like for implication, modus ponens, and the construction proof of negation or the AND. But also Coq offers some user mechanism for proof search. For example, you can ask Coq for do from proof search for arithmetic, reverse arithmetic, first-order logic, polynomial system, ring field, and also you have a general mechanism for calling external oracles. The common base of all these tactics is that there are procedures which take a proposition as input and which construct a proof term, that is a program of the given type, of the given proposition. And then these proofs are checked by the Coq system. So up to now, I spoke about deduction. But in proofs, there is a very important notion, which is computations. And this notion is coming from Egyptian. So at that time, deduction was unknown. The only way of doing proofs was computations. And then we moved to Greek, where we moved to the other extreme, that is only using deduction rule, no computation at all. And 1 century ago, during this crisis of foundation of mathematics, computation went back. So it started with the Hilbert problem, which was, is it possible to state mathematical statements as computation problems and then to solve them automatically? And today we know that not. It's not possible to solve them automatically by computation, all the mathematical statements. But still, we can solve some of them. So this is the Poincaré principle. Is 2 plus 2 equals 4 a proof or just computation? If you go to Presburger arithmetic, so where here you have 2 axioms of this logic, then 2 plus 2 equals 4 is a proof, is a full proof. Okay, here's this big tree, where you have to apply 2 times this axiom and y times this one. But if you start to orient this axiom from left to right, then 2 plus 2 will compute to 4. And then a proof of 2 plus 2 equals 4, it's no more a proof. It's just the application of reflexivity of equality. Okay, because, yes?
Now, doesn't it really depend on what you define as proof? You are doing a rewriting.
No, it's not a rewriting.
Rewrite rules and then applying rewriting rules.
No, it's not a rewriting here. I am not here. I am applying rewrite rules. Because I'm replacing equals by equals. So I'm really applying rewrite rules. But here, the computation is embedded in the logic. So yes, you compute using rewrite rules, but this is something which is decidable.
So your point is you add rewriting as a proof rule. As a proof rule.
You can see like this, yes. But it's really telling that in a proof, you want to remove all these computational steps, and you want the computer to find them. You want the computation to hide what the reader is doing implicitly while reading the proof.
There's another part that this example doesn't or that's implicit in this example, which is representation. So in this example, you represent natural numbers as piano numbers, and so computation on piano numbers might be more efficient than proof on piano numbers, but computation on binary represented numbers.
You can do the same on binary numbers. You can define the computation is pre-arithmetic using binary numbers, and yes, you will be more efficient. But
then there's a question of whether the representation is opaque or transparent to the proof.
So yes, when you are doing formal proofs, the question of representation of your mathematical objects, it's central to your proof, yes. You have to take the representation which exhibits the good structure for doing right computation easily during your proofs, yes. So it's not like in math. So we are moving from math where you are considering every object up to an isomorphism. Here, no. Here the computation is intentional. So you choose a representation and you stick to this one. And if you want to change the representation, you had to do it explicitly. Yes, I agree.
I'm sorry, I didn't really understand what you meant by computation. See,
it means that this is something. So there is a function taking your expression, a computable function taking your expression and returning a result. And what you do, for example, here, when you apply the reflexivity, so on the left hand side you have 2 plus 2, on the right hand side you have 4. And if you are here in Presburg arithmetic, these two terms are different. So you cannot apply the reflexivity lemma because you need x and x on both sides. Here, you will identify terms equal up to computation. So you will apply the function to 2 plus 2 of evaluation, the one to 4, and on both sides we'll obtain 4 and 4. And then you can apply reflexivity.
But you're somehow saying that computation is independent of all this proof business. But how can that be? Because, I mean, that computation somehow knows the semantics of what 2 means and what 4 means and what plus means.
Yes,
how did it know all that semantics? Those semantics are all in the
here. I took you take the axioms and you do a compression. So here you orient from left to right. And so the computation is correct with relation to the initial semantic.
So there's no proof needed? It's correct by construction?
It's correct
if you prove that this function terminates, you're done?
Yeah.
That's all you need to prove?
Yes.
That for this system of oriented rewrites that you will terminate?
So you do some completion and you obtain, so it's the completion complete, you obtain a strongly normalizing system. And yes, you apply this computation function to the term. And so it seems, so on this simple example, 2 plus 4 equals 4, it seems quite trivial. But it means that in a proof, you can change any proof construction by the decision procedure deciding your problem. And so Coq, which is based on the calculus of construction, integrate computation in the deduction machinery. So you have a rule telling that. So if in a proof environment, for a proposition big T, you have a proof small t, and big T is convertible to T prime using some computation, then small t is also a proof of big T prime. And so this tilde here, which convert two terms T and T prime, express the computational power of the system. And so the more you add computation in that rule, in this tilde, the more your logic is expressive. In the calculus of construction, the only things you have in the conversion rule is beta convertibility, meaning evaluation of functions. So here, for example, plus is not, you have to encode plus, and then plus is not evaluating. So when you have 2 plus 2, the 2 plus 2 is fully evaluated. So next, so this is a big step. Coq moved to the calculus of inductive construction, where you can define inductive data types and function by induction. So for example, you can define the natural numbers as being the smallest inductive type, having 0, and the successor function. And then you can define addition by induction of the second argument, for example. And so we obtain the Presburger arithmetic with the equation oriented from left to right. And you will have that successor of x plus 2 is convertible to x plus 3. But what you won't have, for example, is that 0 plus x is convertible to x, because plus has been defined by induction of the second argument, and so you have no rules when, for example, here this x is 0. And so my work here, so you have some little steps next, increasing this computation power. And my work here will be to give a big, to have a big step, having much more computation power in this conversion. And so before introducing CoqMT theory, I will do a small demo. So this is a Coq top level. So I did import some modules, and I will start with doing some propositional logic. So for example, I want to prove that for any proposition ABC, if A implies B implies C, then A implies B implies A implies C. So I start my proof. Okay, and I have a proof environment with the proposition and what I have to prove. So first I start to introduce my hypothesis, and then this is what I have to prove. So I'm starting from the conclusion, going to the hypothesis. So for example, if I apply this is a function giving me a C from a proof of B and a proof of A. So I do some application, and I have two sub-goals, one for A and one for B. A, I know how to prove it. This is an assumption, so I say exact. Now I'm moving to B. B, I know how to prove B from A, so I'm applying this lemma, and now I have to prove A, and done. And so these tactics here, they built a proof term for that proposition. So when I do the QED, what's going on is that Coq is building the proof term and sending the proof term to the Coq checker. And I can print it here. This is a proof term. So this is taking function, taking three proposition, the proof, and returning some application. So this is the same proof, fact 2, but now I'm using some tactic for tautology, first order tautology. And this is direct. And I can print the proof term here, and I have a proof term which is equivalent to the previous one. And so as I said, for example, there is some automation for arithmetic. So I want to prove that for all Mn, then that this statement holds. So I could do it by hand, but I can use the omega tactic and the same. This is done automatically. And OK. So this is done by computation. Okay, here you see there is quite a big proof term. And now, okay, let's go to this 2 plus 2 equals 4. So I can do the proof like in Presburger arithmetic, meaning doing rewriting, replacing equals by equal. So from 2 plus 2, I move to 2 plus 1, successor of 2 plus 1. Then I move to successor of 2 plus 0. Then I replace 2 plus 0 with 2. And then now I have 4 equals 4, reflexivity, done. And so here we have, okay, we have really the proof in Presburger arithmetic with all the rewrites.
All the proofs you just mentioned in 2 plus 2, the sub-proofs, sub-lemmas in 2 plus 2 equals 4, they're all justified by induction?
No, not by induction here, because everything is closed, so I can apply the lemma finitely to prove it. If I want to prove that for all x, y, successor of x plus y is equal to successor of x plus y, yes, then I need to do an induction, yes. But for 2 plus 2 equals 4, the proof is not using induction.
So it's using this thing that you were referring to as computation?
Yes, really the proof of 2 plus 2 equals 4 is this one. I'm moving from 2 plus 2 to successor of 2 plus 1 to successor of 2 plus 0 and then to 2 plus 2.
So that thing for all x plus sy is equal to s of x plus y?
Yes.
Where did you get that axiom from?
So this is proven by induction, yes. This one is proved by induction. Yes.
But that is sort of like already proved, it's in the library, you didn't have to...
Yes. But the proof is very simple. So the proof is not, it's not built in the system. That is, Coq is coming with libraries. And the libraries is having some natural numbers, and you have all the basic lemmas on natural numbers. So the one of Raspberry arithmetic plus some extended one, associativity of addition, and the like. Yes. And so since you are in the calculus of inductive construction, for example, this one is not done by induction. This one is simply one step of computation. The one done by induction is the one where the successor is here. So as for other theorems, I can use some automation, for example, the ring tactic, and then I continue to have some big proof here, okay, for 2 plus 2 equals 4. But I can use some computation, and here I'm using reflexivity. Okay, and this is just x equal to x. And if I look at the proof term, now the proof term is very small. Okay, there is nothing that's saying that this is a proof of 4 equals 4. And then Coq is computing 2 plus 2 to 4 and is validating that proof. So for example, if I want to prove 2 plus 3 equals 4 by reflexivity, then Coq is complaining, telling that he cannot unify 4 to 2 plus 3 up to computation. And now we're entering the real stuff of that work. So SSReflect, which is here the library I'm using, is coming with some libraries about rings. And so I'm adding some more natural numbers. And here I can define two matrices. So the first one is a matrix over the ring R with n rows and m columns. And M2 is a matrices over the ring R with m rows and p columns. And so here matrix is a dependent type. The matrix is depending on the base ring and on the number of rows and on the number of columns. And here the star m is a matrix multiplication. And what I will see is that if I do m1 times m2, what I obtain is a matrix of size n rows and p column. If, for example, I want to multiply m1 with n1, Coq will complain because the dimension of n1 is not valid for multiplication with n1 on the left. So here dependent types is forbidding me from multiplying matrices of the wrong size. And so I can see this in the type of the multiplication, which is telling that I take a matrix of size m times m and a matrix of size n times p, and what I return is the matrix of size m times p. And let's take now a very simple function, so the row matrix. So the row matrix is taking two matrices of size m times n1 and m times m2 and returning the matrix with the two matrices glued together, so of size m and n1 plus m2 columns. And now we define three new matrices, b1, b2, b3, with respectively r1, r2, r3 columns. And I can check, for example, the type of row mx of b1, b2, and this is a matrix of n rows and r1 plus r2 columns. And which is interesting is that if I compute this matrix, the number of columns is r1 plus r2 plus r3. But if I do some associativity, meaning gluing b1 with b2 and b3, then now the size is r1 plus r2 plus r3. And so the number of columns is equal. I can prove that this number is equal to that number. But now what I want to state is that b1 and b2 glued together with b3 is equal to the matrix b1 glued with b2, b3. So I want to prove this. And now Coq is complaining. I am not able to state that lemma because it's telling me on the left, you have a matrix of that size, and on the right, you have a matrix of that size, and the types are not equal because here you must have the same type on the left-hand side and the right-hand side up to computations. And here the two terms are open. They are fully computed, so they are not convertible. And the Coq is rejecting this. So if I want to express this simple lemma, because this is a simple lemma, if I want to express this simple lemma in Coq, then, sorry. Then I must start to use some cast. So here, the cast is taking two proofs of equality, is taking a proof of n equals n, and a proof of associativity of addition for R1, R2, and R3. And then it's telling that the first matrix is equal to the second one, but I'm doing some cast. And if I look at the type of cast, it's really a function taking a pair of proof of equality between m and m prime and n and n prime, and casting a matrix of size nm to a matrix of size n prime m prime. And I won't go into the details of how you can prove that lemma. That's encoding the lemma you want. But handling cast is quite hard because you start to manipulate proof and you have to start off speaking about equality between proofs. And Coq modular theory is here for removing the need of having cast for expressing such statement. So this problem is well known, and some solution has been proposed. So one solution is the extensional calculus of construction. So here in the conversion, so you have the function evaluation, beta convertibility, and you say that any term which are probably equal are convertible. So this solves the problem. You can prove that associativity of addition, so any terms which are different up to associativity will be convertible. The problem is that it's too powerful. For example, 3 will be convertible to the smallest integers, smaller natural numbers, validating the Fermat theorem. And you will not be able to encode basically the decidability in type theory in Coq, so in set theory. So it's too powerful. You are losing proof checking. Our Coq is here for checking your proof. So if you are not able to prove to check your proof anymore, then you are losing the point of Coq.
What is the complexity of proof checking that's implemented in Coq?
In what term?
Meaning like polynomial, exponential?
Yes, but of the size of the...
Size of the input proof.
So exponential like ML.
It's exponential?
Yes, because ML type checking is exponential, and Coq type checking is stronger.
And what's the upper bound?
But I don't know.
I mean,
it's linear in the type.
Type inference is exponential because you have you're inferring types, right, with Hindley Miller and stuff. But in the kernel, you're not doing inference, right? You have fully decorated.
Yes, but it's linear in the type, but it's exponential in the term. But in practice, even for terms where you are polynomial, the constant is the power is very high. So sometimes you have to change a bit the way you prove things to have a proof checking working in practice. So Coq modular theory, so which is the work now, my work I'm introducing. So it's an extension of the Coq formal language. It allows the introduction of decision procedures. So in the conversion rule, it is implemented and will be in the main line of the main version of Coq. And as I will describe, you can still trust this Coq version, although you are introducing decision procedure in its kernel. So for that talk, I will present a restriction of the Coq modular theory, which I call the calculus of Presburger construction, where instead of introducing any decision procedure, we'll only be able to introduce a decision procedure for the Presburger arithmetic. So the calculus of Presburger construction will be a consistent extension of the core logic of Coq. So we'll have function evaluation, the convertibility. You will have the recursor for natural numbers for being able to define inductive types and function over natural numbers. You will have a decision procedure for Presburger arithmetic in the conversion. You will be able to, the decision procedure will be able to use the equations which are available from the proof environment, and the type checking, the proof checking is decidable. As I said, here I want to add some power to the conversion rule. So the only things I will modify in the formal language is a conversion. So that is that relation. And that relation, so will include beta convertibility, function evaluation, recursor for natural numbers, so for fixed point and match. So this is not changing from standard Coq. And then I will introduce the validity entailment for the Presburger arithmetic. And what we want at least is that the conversion must consider equal any pair of Presburger equal algebraic terms. So what I call algebraic terms is any term, Coq term, built from 0, successor, and plus, and variables with the right arities. And for instance, if here I take the dependent type of list of size depending on their size, so on the natural number, so this will solve the motivation example, telling that this type now is convertible to that type because that subterm is algebraic. It is built from plus and variables. This one is algebraic. And n plus m and n plus n are equal in the Presburger arithmetic. And this could be a first definition of Coq with Presburger arithmetic. But this does not define a sound logic. Why? Because let's take that function. So I take a function taking n and m, two natural numbers, and returning some list. And so the type is for all n m of type nat, I return a list of size n plus m, because body is built like this. Using my new conversion rule, I know that this function is also of type for all n m of type nat. Then I return a list of size m plus n. But now, I apply that function to these two natural numbers. The identity function applied to n1 and n2. And this one is not algebraic. And so the type of this function now is list of size, identity applied to n1 plus n2. And I want it to be convertible to the list of size n2 plus identity of n1. But since ID of n1 is not algebraic, then nothing ensures that I can deduce that conversion. Because now the Presburger arithmetic is not able to speak about that subterm. So what I do is what is done in, for example, when you are mixing decision for procedure for different theories into one, that you will use equation, you will use variables to abstract aliens, to abstract subterms which are not algebraic, to communicate with the decision procedure. So if I take so that term, list applied to plus, which is applied to two non-algebraic terms, I will call that some alien. They are not known, they are terms which are not known by the Presburger decision procedure. And what I will do is that I will abstract aliens by variables. For example, f applied to nat and n2 will be abstracted by the variable c1. And this alien will be abstracted by the variable c2. And this row with a here is the algebraization process, replacing aliens by variables. So for example, here, what I obtain is list applied to c1 plus c2. Here I do the same, but now the aliens are swapped. So the algebraization process will give me the type list applied to c2 plus c1. And now, these two ones are convertible. So I'm solving the previous problem, but still, that's not enough. Because I want this conversion relation to be transitive for easing the meta-theory study and for proving that this is decidable. So the question is that which variable we want to choose when abstracting aliens. So let's start from the list. Now list is applied to plus, and the first operand is f applied to n1 plus 0, and the second operand is g applied to n2. So since I know that n1 plus 0 is convertible to n1, this is convertible to that term. That is list applied to fn1 plus gn2. And now, doing some abstraction, okay, I know that C1 plus C2 is convertible to C2 plus C1. So abstracting this one with C2, this one with C1, I obtain this new type, which is convertible to that one, which is G of N2 plus F of N1. And then here I use the conversion 2 times. If during the algebraization process, I choose my variable such that two aliens, you assign the same variable to two aliens which are convertible, then what you will do is that to C1, C1 will represent both the alien f applied to N1 and the alien f applied to N1 plus 0. That is replacing this one and that one. To C2, you assign G of N2. And then, again, what you have is that the algebraization of the first one is list of C2 plus C1, C1 plus C2. The algebraization of this last one is list of C2 plus C1, and then they are convertible in one step. Now, what I want also is to be able to use equations from the proof environment, meaning that if I know that x is equal to 2 and z plus n is equal to 5, I want that to be convertible to this. So what you do is that before doing the conversion, you are looking at all the equations, you extract them, and you send them along to the goal you want to solve. Of course, for the exact same reasons, you want the equations extraction to be subject to alien abstraction, meaning that if I replace z by identity applied to z, and if I replace n plus z by n plus identity applies to z d plus 0 plus n, then I want to abstract this alien and that alien with the same variable. So for proof context gamma, what I will write EQ of gamma will be the set of all the equations I can find in gamma, including equations which are not fully algebraic. And now my conversion relation, which was written with a simple tilde, will be written tilde gamma, which denotes the conversion under the equation I can find in gamma. One thing to notice is that equations will be introduced by the for all quantifier. So, meaning that, for example, if I start with that proposition, that function, which takes a proof P of the proposition x is equal to y, and returning a list of size x, then this must be convertible to that type, which is the type, yes?
I'm sorry, go ahead and finish.
Okay. To the type, taking the same proof for the property x equal y, but returning a list of size y. And why do we want this? That after the for all quantification, you must be able to be you want to be able to use the equation, which is bound by the for all quantification. That is, when you convert this list of x to this list of y, you can use that equation, and then you have conversion.
So in the Nelson-Oppen architecture for communicating theories, you require that that each satellite theory be able to derive all the implied equalities in order to communicate, and then you also have this variable introduction. All right. So here you're not placing such a. You just have this theory, and which. So I'm trying to understand the relationship. It seems similar in some senses, but you're trying to figure out the equalities implied.
So
automatically here, or
so the restriction you have in Nelson-Oppen is to be able to implement it. Sure, I'm speaking for the moment about a validity entailment, which is complete by essence. So it's why I can say I can say that I can abstract I can decide if I should abstract these two aliens by the same variables. The entitlement relation is giving me this transcendently. When I want to implement this, then I need the same restrictions. Yes. So this slide will highlight your point, meaning that this is not an algorithm for the moment. So here we have all the ingredients to give an abstract definition of this relation, tilde gamma. So first rule is telling me that I want the beta for a function evaluation and the iota conversion for the fixed point evaluation. Then here, this is the one integrating the entitlement relation. And so the point here is that, for example, when I'm doing the algebraization of equations, I do not need to know S, because the algebraization is a global process that is taking all the terms of the calculus of construction, splitting this set into equivalent classes for that relation, and assigning a different variable for each equivalent class. So here we are not speaking about implementation. So it's telling me that if I take all the equation of gamma and I do this general algebraization, and using Pressburger arithmetic, I can derive that the algebraization of S is equal to the algebraization of T. Okay, then I can deduce that S is equivalent to T. And then the last rule is speaking about this contextual rules, meaning that if I know that this is equivalent to that, and this is equivalent to that under the extra equation T1, then the four terms here are equivalent. And I have a set of contextual rules, contextual rules like this for the remaining type constructors. So what you have with that calculus is that this is a consistent calculus. You have strong normalization of beta, strong normalization of iota, and you have substitution. You have all the properties you expect about that calculus. And so now you can prove that you can express tilde gamma via an algorithm. So what the algorithm here will be a very naive algorithm just to show that you can decide tilde gamma. So the first point that extracting a equation is very easy. You just search for any term of that form in the proof environment, and you extract them. So now the next point is how to express tilde gamma. So we'll start. I will show this with an example. So I have my typing environment. I have two equations. I have D equals E for natural numbers, for variables, and I have that T, which is a context in which C appears, is equal to the same context in which E appears. And I want to prove that that term is equivalent to that function, returning a list, applied to n. So since now I know that reduction is strongly normalizing, I'm first doing a head normalization of my types. So this one is already head normalized, and this one is a lambda applied to an argument. So this reduced to list applied to TD plus n. And then I have a hat here, which is non-algebraic. And I do some syntactic equality between the two hats. If they are not syntactically equal, then I reject the conversion check. And so since they are syntactically equal, they have subterms, which are paired, which are algebraic, which has an algebraic cap at least. So on the left-hand side, I have n plus t of C. On the right-hand side, I have T of D and N. And so now I will start a conversion check between the paired algebraic subterms. So this is here, I have only one such check, which is this one. And my equations are this one. And so I will now abstract my aliens by doing a pairwise comparison of all the aliens between them. Okay, so I will, for example, check this one with this one, this one with this one, this one with this one. And what I obtain here is that T of D is convertible to T of E because I know that D equals E as an equation. So I will abstract TD and TE with the same variable. TC is not convertible to TD or TE or any other alien. So for TC, I will use a different variable B. So now what I have to check is that n plus A is equivalent to B plus n, knowing that D equals E, and after algebraization that A equals B. And of course, this is validated by the Pressburger arithmetic. So I deduce that my initial terms are convertible. So now, why should you trust my implementation of this kernel? First, the real implementation is not using this naive algorithm doing pairwise comparison of aliens, but doing some constraint-based algorithm. And so I said that you trust Coq because the kernel is 5,000 lines of code. And here, I allow you to bring some decision procedures into this kernel, which can be big, which can have aggressive optimization. And so you break the trust, unless the decision procedure is generating some certificates. And so what you can do is to define a two-level kernels. So what I call CC of X is a type checker, the kernel for the calculus of construction, with some decision procedure X in its conversion. So this is the kernel, this two box. The kernel has two levels. You have CC of MT, which is the calculus of construction without any theory, with the empty theory, meaning the old kernel, the one you trust. And CC of T is a Coq modular theory with the embedding for the first order theory T. Okay, and this is the one you do not trust. And okay, you want to check that P is a proof of that, of this list of size n plus n prime, and this list of size n prime plus n. And so you send that to the kernel. At some point, the kernel will have to do some conversion check, and this conversion check will do a call to the decision procedure, asking if n plus n prime is equal to n prime plus n. And the decision procedure is answering this third step, yes, it is. But I've given you a certificate, and this certificate is a Coq proof T of n plus n prime equals n prime plus n. But this statement is expressible in the old kernel. This one is not. Okay, this is the same problem as for matrices. But this one is equality on natural numbers and is expressible in the old kernel. So I can send this proof T, the certificate, to the old kernel one, CCFMT. And if my decision procedure has no bugs, then the Coq kernel should have to answer me, yes, this is a valid certificate. And then what I did here is that in this two-level kernel, I reduce the trust of that part to the trust of this one, the old one. So I still trust my kernel as long as the decision procedure is answering with certificates.
So do you really reduce everything to CC of 0? Because the checking of the statement in 1 still involves the rules of CC of t, right? It's only the proof of the equality that gets reduced.
Yeah, so in CC, in the implementation of CC on 0 and CC on t, the only thing changing is a convertibility check. All the remaining is the same algorithm. Meaning what you have is that in CC of 0 you have if I have a theory, and in the CC of x, I mean you have if the only difference between CC of x and CC is that if the theory is empty, then I'm doing beta convertibility. Otherwise, I'm using this extra decision procedure. And so you can read this, you can trust this, and then the part I am using the external decision procedures. This part you do not have to trust it because you reduce this one to the old code.
Okay, so this I believe that I don't have to trust t, I believe, but I just have to trust CC of t plus CC of 0.
No, you have to trust CC and MT plus the function doing the branching between CC and MT and CC of t.
And that function is part of CC of t?
That function is part of CC of x, yes.
Okay, CC of x, all right, yes.
And still, so I don't have time to expand on this, still, and then you can remove CC of t if you modify CC and MT with an extra constructor with implicit cast. Which is a calculus between CC and CoqMT. And this CC at MT plus implicit cast is very small. So the idea here is that you want to remove this one. So let me conclude. So in this call, I presented Coq module theory, which solves a long-standing theoretical problem that is using an extensional equality decided by decision procedure in type theory. In this extension, the kernel becomes incremental. New theories are added, and they come with certificates, and the certificate checker can be added safely by the user, then reducing the trust in the kernel to the old one. This improves a lot over pure reflection Boyce solution, because you have more typable terms. That is, it's not only that CoqMT is adding more automation, it's that you can express more statements without relying on coding, like the cast. It allows an easy use of dependent types. So I show this about matrices. Now, for the row MX problem, you can state the statement as you want it to be stated. And also, CoqMT is implemented and it's freely available on that address. CoqMT will be integrated in the next major release of Coq. And CoqMT has been used already in several developments. For example, I have one example of formalization of combinators for logical gates, where a gate is depending on the number of inputs and the number of outputs. It has been used for encoding of mathematical construction, like taking the countable union on a monotonous set of monotonous family of sets, for example. And CoqMT meta theory has been studied carefully. Currently, we have a syntactical model of the core logic of CoqMT, which has been mechanized. And we are also mechanizing a set theoretical model in Coq directly. And you can find more information of CoqMT in that conferences, which describes the system's implementation and the meta theory. And for concluding, I would like to give a big picture of this work relating to other work I'm involved in. So here I have my work about Coq module theory. As I said also, when in the kernel, we want to check certificates for ensuring the security. And so for that, we need fast evaluation of function in Coq. And so this is a second part that you may not trust in the kernel, which is the part which is compiling Coq terms to binary functions that we evaluate. And so we are currently working on certifying the kernel compiler of Coq. And also, this work is related to the F-star language. As I said, I formalize and mechanize the meta theory of F-star in Coq, and also I certify its core type checker. But F-star is using, for example, the Z3 SMT solver. And so I work on some problem on validating certificate generated by SMT solver. And also, F-star is used for doing some protocols formalization. And we are working as a use case as a TLS formalization from high-level APIs to cryptographic primitives. And for that, there are two related works, which are the formalization of the maths behind cryptographic primitives, for example, elliptic curves, and also some extension of F-star to some relational type theory that then will be integrated into Coq. And why doing all of that? That is why now formalizing all these tools and going to big use case is that I think that we are moving from formal tools which were not usable even by experts to formal tools which now are usable by experts for formalizing big programs. And I think now we need big use cases because now we need to find how we can move to formal tools usable by engineers, for example. Thank you. Yeah.
So can it happen that your decision procedure says that, yes, I have proved this, but the whole enterprise fails in the proof checking part?
Yeah. So if there is a bug, the certificates must be wrong.
So, but you think that can happen only when you have bugs in your software, or is there a theoretical reason for it that you can't guarantee that whatever work that decision procedure has done can always be expressed in the in whatever this business is?
I really think that the logical expressiveness of Coq is more powerful than what you can express in decision procedures. Basically, in Coq, you are more powerful than set theory. So it will be very unlikely that a decision procedure is deciding something for a theory which is more powerful than Coq. So there is no reason that you cannot encode your certificate. It doesn't mean that it will be simple. And perhaps this procedure of rebuilding a certificate for the result of the decision procedure will be a lengthy procedure, yes. But you should be able to do it.
Perhaps you can prove it too, right? That you will always be able to do it.
Yes.
For a given decision procedure.
Yes, you can. So the problem is that you do not want to lose some time on that. Meaning each time you will add a new optimization in your decision procedure, you will have to update the proof that your decision procedure is correct. And for example, for SAT solver, you have to add optimization every year, because if not, you are losing the next SAT competition. So you do not want to have to, because proving that all the optimizations are correct will be, I think, will be complicated. And that's why all the community is moving from certified decision procedure to decision procedures generating certificates. But for example, for SAT in Coq, you have AlterGo, which is a decision procedure for SAT, written in Coq, proved in Coq, and then you can use it instead of Z3. But you will be slower in the end. Yeah.
So the logic for equivalence is classical logic, where Coq is constructive.
Yes.
So there's some.
Okay. If you want to integrate some decision procedure, which is classical, you need the axiom, the exclusion middle axiom in Coq. Yes. It's a choice.
But you do that, right? I mean,
no. For example, for Pressburger arithmetic, I'm not using exclusion middle.
Oh, so you only have constructive.
Yeah.
So I think on the slide you also mentioned that you have inductive definitions as part of what you do for equivalence checking.
Yes.
So how's the integration of the decision procedure, say omega test or Pressburger arithmetic, with inductive definitions, I mean recursive functions?
Badly. So I haven't described this today. But you have to add some new restriction from what I described when you start to have inductive definition for two reasons. One, for example, if you start to use equation, for example, you know that x is equal to 0, and you have a match of on x, then you must be able to replace x by 0 by conversion and then to reduce this, meaning that the iota reduction must be done modulo the theory. In that case. And next, you have also in Coq the ability to construct proofs, to construct types by induction. So I can write a function which takes natural numbers and returning nat when this natural number is equal to 0, or nat arrows nat if not. If I allow expression of an inconsistent set of equations, for example, I have the hypothesis that 0 is equal to 1, then I will have that nat is convertible to this function applies to 0, which is convertible to this function equals to 1, which computes to nat arrows nat. And then now I am able to encode the Russell paradox in Coq with that. So meaning that if you have strong induction, this ability of constructing types by induction, you must restrict the expression of equation to only consistent set of equations. Yes.
I was actually wondering if there were some decision problems in the space of recursive functions plus arithmetic.
No. So theoretically, it's decidable. In practice, for example, I added some restriction to be much more efficient. For example, this reduction modulo the theory is very inefficient. But as we want to use decision procedures to do some conversion for dependent types, and list is a symbol which is not defined. It's a type constructor, so it does not reduce. So I know that list applied to a natural number won't put the natural number in the place of a match. So I know that, for example, in that place, I can allow the conversion. But I will forbid the conversion in other places, which can put the arguments in the context of a fixed point or a match. So yes, there are much more restrictions. The full definition of the calculus, it's more complicated from what I presented. Yes.
So with the extensional equality, you can show that if you prove two things to be equal, that you can substitute them like that in, for example, the types. What about if you co-inductively prove that two things are equal by, yes, by simulation? Can you then substitute them in the same way?
Let me think. So co-induction in Coq first is not well defined, but you should be able to. But I have to think about this more precisely. But at first glance, I would say yes.
Any other questions? No. So thanks, speaker again.
Thank you.